Right? And I'll be talking about expanders. Everything is finite in this talk, as opposed to Aviv's claim that this in infinite series of expanders. So the expanders are finite. So it's based on several results of mine with several co-authors, but mostly it's a joint work with Limor Friedman, who is my master degree student, and she's depicted here actually talking about this very subject at a conference. Good, so let me start by giving you some general background, or maybe rather by doing some propaganda about expanders. Not sure it's needed in this audience, because expanders are omnipresent. They're very familiar to most people in the field. Actually, there are several people in the audience who have been making their living of expanders quite successfully, so-called founding fathers. And not clear, I really need to convince you that expanders are expotent, but let me still say a couple of words about it. So what I mean by an expander, the definition, it's not exactly a definition, but informally, we have a graph G with vertex at V and edge at E. And we say that this graph is an expander if every vertex subset U of cardinality at most half the vertices, its external neighborhood is large. Now, of course, I need to specify what I mean by large, and the essence of a definition is exactly in this specification, how large is this large. Let me postpone it for later. I will, of course, give you a concrete definition of an expander. But that's a spirit of things here. And that's a really very important notion or subject in combinatorics. It's omnipresent and appears in all kinds of places. It's all over the place in extremal graph theory. It's a subject of study by itself, extremal properties of expanders, etc., etc. It's used in given and explicit constructions of random like pseudo-random graphs. So expanders and pseudo-random graphs are synonyms in a sense. It's used in Ramsey theory. It's used, and actually that's probably was the original, some of motivations for inventing expanders. It's used to design, in particular to design lean but strong networks, etc., etc. And the list is very long. And you can consult, for example, the survey of Aviv and Nati Linial and Shlomo Khoury about expanders, which gives a lot of theory and a lot of application as well. So that's really a very important subject, and it's of course too wide to cover it in full. And therefore, what I'll be giving is I'll fix some concrete definition of expanders. And this definition is rather on the qualitative side of it, and it's fairly relaxed in the sense that I won't be shooting for the best possible expansions, and won't be asking myself what's the best possible expander given some definitions, some restrictions, but rather I would assume that my graph is a fairly decent, but perhaps not the strongest possible expander. And that's how I will set my definition. And then I will start studying properties of these expanders as defined as the way I will define them. And mostly I will talk about extremal properties, and between those properties are long passes. How long a pass can I find in such an expander? How long a cycle can I find in such an expander? Or more generally, what can you say about cycle lengths in such expanders? Of course, you can study more of it, and this definition is rich enough to allow for some further properties, and further properties which I won't be covering in this talk, but they are worth studying. Existence of minors, for example, existence of small separators, etc., etc. And if you are interested in the subject, I can refer in particular to my relatively recent survey, which is called Expanders, How to Find Them and What to Find in Them. And it's in the proceedings of the British Combinatorial Conference from last year. So there's stuff which I'm presenting here and much more about this, and you are welcome to consult it and to study more about this subject. Very good. Let me now define what I mean by an expander, and I call it an alpha expander. Okay, so what's an alpha expander? So suppose we have a graph AG with vertex at V and edge at E, and we have some parameter alpha, which is a fixed constant. Think about 0.1, for example, but before it, I need to introduce some standard piece of notation. Suppose we have a graph G, and we have vertex subset U. As usually, we denote by NGU, and when G is clear from the context, we will omit this index. So NU is all vertices outside of U, which have at least one neighbor in U. That's the so-called external neighborhood of U. Okay? And now we can define the notion of an expander. Suppose we have a graph, and we have a parameter. So we say that our graph is an alpha expander. So alpha is a quantitative measure of expansion if the following holds. You look at all subsets of vertices of size up to n over 2, and for each and every of them, you postulate that it expands outside by a factor which is at least alpha. So the neighborhood, the external neighborhood of every vertex subset U, which is at most half the vertices, is at least as large as alpha times the size of your set. Okay? Now, I stop here at n over 2, partially because of convenience, partially because you cannot require a very strong expansion from sets which are very close to being everything. And therefore, we should stop somewhere, and stopping at the middle point, n over 2, is a decent enough option. Already by itself, it delivers a lot of properties, which I will state immediately. So that's my definition of expander, and mostly it's not a big deal, as you can imagine, to construct an expander which is dense. For example, I can just take a complete graph. The idea would be rather to construct something or think about something which is sparse. Sparse means has a linear number of edges, or maybe even maximum degree bounded by some absolute constant. And as I said, you should think about alpha as being some small constant. For example, alpha is 0.01. And actually, I'll be studying the properties of my expanders in terms of alpha. I'll be thinking of alpha as some kind of function which tends to 0. And I'd like to know some particular properties of my expanders given this behavior of alpha. Very good. Now, if you define definition, as usually, you should make sure two things are in place. One thing is it has a meaning, which means it enables you to derive some further properties. And the other thing is definition is not vacuous, meaning there are creatures in the world which subscribe to this definition. So let me describe it briefly. And indeed, the alpha expanders, as I define them, has some basic nice properties. The first property is fairly simple. If you look at an alpha expander on n vertices, and if you take any vertex v and start growing balls around this particular vertex, the ball bk of v is all vertices at distance k from v. That's my notation. Then these balls are easily shown to grow exponentially. The size of the ball of radius k around every vertex v is at least as large as 1 plus alpha to the power k. Of course, you need to cap it by something from above. And therefore, technically, we are taking minimum between 1 plus alpha to the k and n over 2. And that's fairly easy to prove. We just prove it by induction. And that's already nice enough because, for example, from this property alone, you derive that every alpha expander is a connected graph. Because if you take two vertices and start growing balls, after logarithmically many steps, the balls will be of size more than n over 2. And therefore, they intersect. This in particular shows that not only the graph is connected, but it also has a logarithmic diameter. Another property which you can define from definition is if you run a random walk on your expanders, it's not a subject of this talk, therefore I will be brief here, then what you get is a rapid mixing. Technically, you need to assume bounded maximal degree here, because otherwise you can stuck in a dense and small set. But if you assume that the maximum degree of the graph is bounded, then a random walk on an alpha expander converges to a stationary distribution in logarithmically many steps, which is also a nice feature. You can also prove quite fairly easily that in such an expander, all separators are large. An alpha expander has no sublinear separators. And because of this, and not just because of this, you can in particular talk about embedding minors, and you can argue that every alpha expander contains large enough minors, which is nice. And in the rest of the talk, I will be talking not about these properties, but rather about paths and cycles. But the definition is rich enough to support some other properties as well. Okay? And the list is very long. Okay, so definition is meaningful, and now we still need to check the definition is not vacuous. There are alpha expanders, and of course there are. And the simplest way to get an alpha expander is just take a complete graph, which is very boring. You can do the next step away from this bottom, and you can take a complete bipartite graph with unequal sides. One side is of size alpha n over 2, and the other side is of size n minus alpha n over 2. So that's, of course, an alpha expander. It's fairly dense, which makes it not very interesting. But the point to notice here is that in this expander, there is plenty of substructures, but there are no odd cycles. Which means that if you have an alpha expander, you cannot postulate having cycles of one length. For example, an alpha expander is given here, has no odd cycles, and therefore you cannot guarantee having odd cycles in your graph. And also one thing to notice and to remember as a benchmark for further discussion is that in this expander, a longest path and longest cycle, they have length alpha. Of course, you can specify it if you're unhappy with this dense expansion graph, and there's a reason to be unhappy because normally you would like to have a sparse expander. Then you can specify it. You can increase the smaller side a bit. You can take a side A of size alpha n, a side B of size 1 minus alpha times n, and you can arrange, for example, by taking random edges, a bounded degree fairly strong expander between these two parts, and this will be an alpha expander, and it will have linearly many vertices. So there are sparse alpha expanders, and again, in this example as well, we don't have odd cycles, and the longest path will still be of length proportional to alpha n. Yes?
If I want, I can set alpha 1/2 and make it regular, right?
Sure, but the point here is we don't really want to make it regular, and you will see that actually we will be talking mostly about very, very sparse expanders, which means that typically for quite a few vertices, the degree will be even 2, or maybe even 1, and here and there we'll have vertices of degree 3. So that's a really sparse creature. We are not shooting for strongest possible expansion. I give you a 10 regular graph, and you should arrange it in the best possible way, but rather we assume that our expander is kind of weakish, and we still want to derive some particular properties. And so in this sense, we are talking about fairly sparse graphs, much sparser than regular graphs. Okay, another systematic way of getting an alpha expander, which is kind of interesting, is you can start with a strong expander, and then you can subdivide its edges. And it's given by the following fairly simple proposition. Suppose we have an alpha expander on n vertices, and we assume technically that the maximum degree is bounded by a constant. And then we have a stretching factor L, which is a positive integer. And now what we are doing is we are taking every edge and stretching it by a factor of L, meaning we insert L extra vertices into every edge. Okay? So what we get is a graph. This graph barely has vertices of degree larger than 2. Most of the vertices are actually of degree 2. And still you can prove that what you get is an expander. You lose an expansion, of course, because you make a graph sparse. But still, if you start with an alpha expander, and if the maximum degree is bounded by a constant, what you get is alpha divided by L expander. Which means there is a systematic way to start with a very strong expander, to make it sparse, to make it fairly sparse with most vertices of degree 2, and this new graph will still be a decent expander. Okay? Now let's look more carefully at this example. For example, here, because you subdivide every edge L times, every cycle in the original graph becomes a cycle in the new graph, but in the new graph, all cycle lengths will be divisible by L plus 1. There will be plenty of them, but each and every cycle in the new graph will have its length divisible by L plus 1, which is another restriction, which means that we can still talk about expanders and cycle lengths, etc., but we can wish for more. For example, we cannot wish to have lots and lots of lengths, cycle lengths. Sometimes they can be fairly sparse. Another thing to observe here is that it's a bit troublesome example in the sense that in the resulting graph, you don't have any two vertices which are adjacent to each other and have degree 3. Because your graph is sparse. Okay? And therefore, for example, if you are in the business of embedding and you want to embed a graph H, and your graph H, the embedding target, has two vertices which are adjacent and which have degree 3, then in this new stretch graph, there is no such creature as well, which means that for embedding statements, you cannot really get very far. Even if you are to embed a tree, and even if your tree has two vertices of degree 3 which are adjacent, after this specification, you cannot embed it, which means in terms of embedding substructures in alpha expanders, you should be very, very careful for what you ask. There is a lot of things which you cannot just get there, cannot guarantee there, but still there is a lot of stuff. The talk is very long. I still have some 45 minutes to fill, so there is stuff to be found in such an expanders. Okay? And as I indicated, we can still hope to find lots of other things. So we can talk about long passes, we can talk about long cycles, we can talk about cycle lengths, we can talk about minors, etc., etc., etc. Alpha expander is still a fairly rich structure to investigate and to find some other substructures. Very good. Let me give you yet another example, yet another approach. How can we argue about alpha expansion? And a very nice way is to do it through graph spectrum. And this was what was advanced by Noga Alon and Vitaly Milman 36 years ago, which sounds quite serious. So Noga was very young by then, but wasn't exactly 4 years old. So you can make some approximation for Noga's age. He's still young. And the statement is as follows. So we have a deregular graph on n vertices. And as usual, we look, because we are talking about spectrum, so let's look at its eigenvalues. Eigenvalues of a graph are technically eigenvalues of its adjacency matrix. So we have n by n matrix of zeros and one. It's real. And therefore, it has a full spectrum of eigenvalues. We denote them by lambda 1 out to lambda n. And we customarily order them in the non-increasing order. The first one is easily seen to be exactly equal to d. All the rest are at most d. And actually, if a graph is connected, there will be a gap between the first one and the second one. And those are the so-called eigenvalues of G. So the eigenvalues of a graph are eigenvalues of its adjacency matrix. Okay? And the point is that if you look at eigenvalues, it's enough to look at the so-called spectral gap, which in this case is the difference between lambda 1, which is d, and lambda 2, to guarantee expansion. And specifically what we get is an alpha expander, and the value of alpha is given by the expression alpha is equal to d minus lambda 2 divided by 2d. So technically the proof proceeds by estimating the number of edges crossing between a set and its complement. But since our graph is deregular, if you know that each set emanates outside lots of edges, its external neighborhood better be large in order to be able to accept all those edges. That's how the proof proceeds, which means what we get here is that the eigenvalue gap, d minus lambda 2, guarantees expansion. For example, if you have a three-regular graph, and if you know that lambda 2 is somewhat smaller than d, then you already have a decent expander. Okay? Maybe one thing to observe or to remind you here, there is also kind of a parallel notion of so-called n-d lambda graphs. These are graphs which are on n vertices. Deregular and all eigenvalues, apart from the trivial one, which is the first one, are at most lambda in the absolute values. So n-d lambda graphs are some different creature. N-d lambda graphs are more in the business of resembling pseudo-random graphs. They are pseudo-random, they are more similar to random graphs. So here, if you're interested in expansion only, it's enough to look at d and lambda 2, and we don't need to look at this last eigenvalue. For example, a bipartite graph can be a very nice expander, and a bipartite graph cannot be, by definition, cannot be a pseudo-random graph. So in terms of expansion, what matters here is not lambda 2 and lambda n, but just lambda 2. Very good. Now that we know that the definition is meaningful, and there are some examples of and some systematic ways of getting alpha expanders, we can state the questions we would like to address, and they are as follows. So suppose we have an alpha expander on n vertices, and the question is, what can we find there? And in this talk, I'll be concentrating on passes and cycles in this graph. For example, we can ask how long a path can we find in G, or more challenging question is how long a cycle can we find in G. Okay? Do we have a linearly long cycle always? If that's the case, what's the dependence on alpha in this expression? More generally, we can study cycle lengths. For this, we can define the set L of G to be the set of cycle lengths in G. So that's a subset of 1 up to n. And we can study its properties. We can study how many elements in this set, how well is it distributed, as it's spread nicely enough. Can we approach any given number by this by a member from L of G, etc., etc. So that's the subject of our study. Okay, those are our goals, and now let me start doing stuff and explaining you what I'm about to do. And I need some tool, and the most basic tool is the so-called depth first search algorithm, or DFS algorithm. Presumably most of you will know it, so those who know it just follow it, because I perhaps use a somewhat non-standard notation. So my notation is not exactly Corman lazy and reversed, but you can still follow it. If you don't know what DFS is, that can be at least one message you can get out of this talk. That's a really very nice algorithm. It's less known than its big brother or bigger brother breadth first search algorithm, but it's still a very useful algorithm. Formally, it's an algorithm for uncovering the component structure of a graph, but unlike BFS, which is by its name, breadth first search proceeds by doing it by spreading it in breadths, DFS actually pushes deeper and deeper. And you can imagine that as such, it will be quite useful and conductive for finding long passes and long cycles. And turns out the intuition is not really wrong. So what is it? It's an algorithm for exploiting the component structure of a graph. We start with the graph G. Technically, we need also to give some order on the vertices of G in order to prioritize and to be able to tell that for a given set, vertex V is the first vertex according to this order. So suppose we are given G and some order sigma on the vertices of G. And what we output is a spanning forest F of G such that connected components of F are exactly equal to the connected components of G. Okay, so which means eventually by the end of the day we will uncover the connected components of G. Our goal is actually different. Instead of looking at connected components, we'll be looking at passes and cycles, but formally that's the tool. Now, what exactly does the algorithm do? So the algorithm maintains and updates a partition of the vertex set into 3 parts, which I denote by S, U, and C. S is the set of already processed vertices. U is a set of vertices which are currently processed, and these are vertices kept in the so-called stake, which means a last in, first out discipline. You add a vertex to the last one, and once you're dealing with it, you take always the last added vertex. And C is a set of vertices waiting to be processed. Okay? Of course, naturally, you start with all vertices waiting to be processed. C is everything, and S and U are empty. And eventually, by the end of the day, you need to process all vertices. You end up with S being everything, and U and C being empty sets. Okay, what does the algorithm do? So at some point of time, we have set U, S, we have set U, and we have set C. We look at set U. If the set U is non-empty, you always go to the last vertex which is added to U. Remember that we're using so-called stack or last in, first out discipline. And we look at V, and we scan C for neighbors of V in the order given by sigma. Okay? And if we find a neighbor of V, we take the first such neighbor, which is denoted by U, and we take U and we move it from C to U. Okay? We append it as the last vertex of U. It can be the case that V has no neighbors in C, in which case we know that we are done with V, and we can move it to the set S of vertices which have already been processed. Okay? It might happen now and then, not just in the beginning, that the set U is empty. This actually means that you are about to start a new connected component. Then you go to C, you find the first vertex there, you move it to U, and this vertex starts exploration of its connected component, and eventually you will find its connected component. Okay? So that's the whole algorithm. That's very simple. Let me maybe return it here. So we have S, U, T. We always look at U. We look at the last vertex at U. We look at its neighbors and C. If there is a neighbor, we move it and append it to C based on the order of sigma. If there is no such neighbor, we are done with the current vertex. We move it to S, and then we proceed. Okay? So here's a simple illustration. There's nothing particular about it. Actually, there's lots and lots of applets on the internet which demonstrate you how this algorithm runs. You can use them. In this particular example, we have 2 connected components, and eventually we will uncover both of them. So the algorithm starts by taking the first vertex, which happens to be 1, and then we go 1 to 3 to 8, and then we start rolling it back. We move 8 to S, and then we move 3 to S, and then finally we move 1 to S, and then we are done with this component. Then we get to the next component. We start with 2, and then we are pushing deep. We go from 2 to 4, from 4 to 6, from 6 to 5, and then we start rolling it back till we reach 4 again. Then we go to 7, then we delete 7, and then we delete 4, then we delete 2. Okay? That's an algorithm, and if you follow it correctly, you can see that the important thing is to look here at the set U. Set U fluctuates in size, and it becomes longer or shorter. But the point to notice here, and that's actually one of the nice properties of the DFS algorithm, you always have a path in U. The path can become short or long. You append vertices, delete vertices, but you always have a path. Which means if you're able to argue that during the algorithm execution the set U is large, then you can derive that your graph has a long path.
But generically, this won't give you the longest path, right? So even if you keep track of all the forests made by this,
sure,
you won't get.
Sure, of course you can number your vertices in such a way that you really get the longest path, but there is no guarantee that at any point of time what you get inside U will be a longest path. But still, what we'll be able to argue is that the path given by this algorithm is long enough.
You say things like if you have a random ordering of vertices, you'll get a path that's at least some some function besides the long.
Probably no, but in this particular case, what we'll be arguing is that if you start with an alpha expander, we get a path whose length is proportional to alpha n, which is reasonably good enough. But I would guess that for a random choice.
So any graph that has a Hamilton
But theoretically it cannot be very helpful. You need to assume something about the graph, but in order to get a long path by random order, but for the case of alpha expanders, we are doing reasonably well. Very good. Now, what are the basic properties of DFS? More or less, I'll state 4 of them. 3 of them follow more or less from the definition, and the fourth is nearly equal simple, but it still requires some thought and some proof, which I will give to you. So the first property is at any stage of the algorithm execution, you move exactly one vertex. You move a vertex either from T to U or from U to S, which means that if you need to catch a moment when there will be exactly 127 vertices in S, assuming the graph has at least that many vertices, there will be such a moment. If you need to catch a moment when the size of S is exactly equal to the size of T, there will be such a moment. So the vertices are being moved one by one, and therefore you can analyze as a point of the algorithm execution when the size of S is whatever you need, or the size of S is exactly equal to the size of T. That's very simple. Another simple property is that at any stage of the algorithm, we have 3 sets S, U, and T. They change in time, but at any point of the algorithm execution, the current set S has no neighbors in set T, because S is a set of already processed vertices. T is a set of vertices which are waiting to be processed, and therefore you cannot have an edge between S and T, because otherwise you would have kept processing these vertices. Okay? Which means that S has no neighbors in T, which means the neighborhood of S, the external neighborhood of S, resides entirely inside U. And therefore, if you're able to argue that every set has a large external neighborhood, this shows that the set U at some point of the algorithm execution will be large. Okay? And the third feature is what I mentioned already. Always the set U comes and goes, it fluctuates in size, but at any point of the algorithm execution, what you have inside is a path. And that's immediate, because what you do, if you append the vertex, you append it as the last one, which means you have a path and you add another vertex. If you delete a vertex, you always delete a last vertex of the path, and therefore you still preserve a path inside. Okay? Now, those are basic features, and now that's the fourth feature, which is perhaps less well known, but is nearly equally simple and sometimes quite handy. Actually, with Noga and Paul Zimmer have a paper which is written here, and 20 years ago we used this property for something related to color critical graphs, and here is the feature. So suppose we run DFS on a graph G, we get a forest, and normally the graph you run your DFS on has some cycles. And of course, forest has no cycles, which means normally you will end up with much less edges than in the original graph. There will be some edges which are in a graph, but not in the forest. And the question is, what can be said about such an edges? Okay? So suppose we have an edge E, which is in the graph, but not in the forest. Okay? And the question is, what can be said about such an edge? Okay? What are its properties? And then it turns out that this edge cannot go in an arbitrary way. What you can have is, if you look at the vertices U and V, one of them is always underneath the other in the forest you are creating. For example, having such an edge is perfectly fine. There is an edge going from U, skipping all the way to V, but you are not allowed to have edges going sideways. If the edge is not present in your forest, this edge never goes sideways. It actually resides inside the subtree generated by higher vertex. Okay? And that's fairly simple to see. Suppose that's not the case, then let's assume for simplicity or for definiteness that U is discovered before V, and V is eventually not under U and F. Now, how can it happen? Eventually, you are done with everything. You are done with U, and you are about to move U to the set of already processed vertices. And you are doing it without dragging in vertex V, which is, of course, a mistake, because this cannot happen, because the edge UV is there. And therefore, this cannot really happen. We get a contradiction. This means that there are edges which are absent in our forest F, but these edges cannot go in arbitrary way. They go in some particular way. This will be quite handy in some of our arguments. Very good. And so now let me use this property to argue about long passes and long cycles. Okay, first let's start with long passes. It's in a fairly surprising way. If you haven't seen it, it's what we'll get is the existence of a long pass, and the proof will be basically 3 lines long. Okay? Here it goes. So suppose we have a graph G on more than k vertices, and suppose we have two positive integers k and l, and we know that every set of size exactly k has its external neighborhood at least as large as l. So we assume a kind of single pattern expansion. We assume that every set of size k has a fairly large external neighborhood. Then we can argue that in this case we have a path of length at least L in our graph. Okay? And the proof is very simple. So we run the FS according to G, and we can fix an arbitrary order on the vertices. And then we stop the execution of the process when the set S of already processed vertices has cardinality exactly k. There will be such a moment because we move vertices one by one. Now, what do we know? We know that the set of edges between current S and current C is empty, which means the neighborhood of S, the external neighborhood of S, resides entirely in the middle set U. And if this external neighborhood is large, this means that the set of U is large, set U has cardinality at least L, and U always contains a path, which means what we get here, we get a path of length L. Now, technically, that's the whole proof. Actually. As you see, it's 5 lines, but that's the proof. Okay. So technically, I'm cheating a bit. What we get here is a path of L vertices. But if you think a moment about it, you will be able to add another vertex and to get a path of length L edges here. Okay. So that's the whole argument. So in particular, we derive from here that we have an alpha expander on n vertices. What we get is a path of length at least alpha n divided by 2. Okay. Because eventually, during the algorithm execution, the set S will be of size exactly n over 2. And then this set S expands outside by a factor of alpha. And therefore, at that point of time, what we have in U is a path of length at least alpha n over 2. That's not bad, because if you take this funny example of a complete graph which is unbalanced and with size alpha n over 2 and the rest, what we get here is a path of length alpha n, and here by DFS we get a path of length at least alpha n over 2, which means we are technically by factor 2 at most away from the best possible result. Okay? And we got it fairly cheaply. So we do have long passes. Okay, so let's talk about cycles. Cycles are a more tricky business, but still we can argue not that bad about cycles. And I'm not sure, sorry. I don't know really to improve it. I mean, I have never tried that hard, but I don't quite see how to improve it a bit. But usually, so in this business, basically, we are thinking, I'm at least thinking of alpha as being some small constant, and what matters is dependence on alpha. So here we get linear dependence on alpha, and the constant might be not optimal, but that's what we get. Okay. So let's see what can we say about cycles. Cycles are more technically challenging than passes. And the statement is as follows. We start again with an alpha expander on n vertices, and then we can argue that we have a cycle of length at least alpha n divided by 4. Now, cycles are different from passes because for passes, you can guarantee every path length if you get a pass because length is longer. Here, I cannot really guarantee you any particular cycle length which is longer than alpha n over 4. For example, if you choose to shoot for an odd number, maybe there are not all odd cycles in your graph. But what we can guarantee is that there is a long cycle, and long means of length at least alpha n over 4. Okay? So here's an argument which is was obtained jointly with Noga alone. So again, we run the DFS, and since we assume that our graph is an alpha expander, what we get is actually a tree, not just a forest. Okay. And now you take this tree. This tree has root r, and now you need to find a vertex v inside the tree and a subset of its immediate children x, so that if you look at the union of the sizes of subtrees rooted at x, you get something quite substantial, and something quite substantial means of size between n over 4 and n over 2. Okay? That's actually fairly easy to argue. What you do is you start from the root, and whenever you see underneath a vertex which has a subtree larger than n over 2, you move there. Okay? And eventually, when you are not able to move any further, you are at the right point. You have a vertex v. The vertex v, its subtree including v, has more than n over 2 vertices. And on the other hand, every subtree there has size at most n over 2, and then you can group these subtrees in such a way that the union of these subtrees will be of size between n over 4 and n over 2. That's a very simple argument. I wouldn't even call it number theory. Okay? So let me know this set by u. Okay. Now let's proceed further, and what we do is as follows. So we have a root R, we have this special vertex V, and we have a set U of subtrees underneath it. So let's look at the path P from root R to V. And by the property of DFS, we have this set U. I will show you a picture in a minute. We have this set U underneath, and this set U really resides at the very bottom of the tree. And the external neighborhood of this U has to fall along the path, which means that n of u is a subset of u of p. And therefore, if we are able to argue that n of u is large, and we are able to argue it because we assume that our graph is an expander, and u is substantially large, this in particular means that the path p is long, and not only the path p is long, you are able to jump pretty far away from u along this path. Okay? So let me take this furthest vertex, v star, okay? And it's fairly far, it's a distance at least alpha n over 4. And then we can construct a cycle as follows. We go to its neighbor u, and then we get a cycle, and this cycle is constructed as follows. You go from u to v inside p, then you go from v to v star along path p, and then you jump back to u. And what you get is a path of length, a cycle, sorry, at least alpha n over 4. So here's the picture. We go from R to V. Underneath V, there is a clump of subtrees of cardinality between n over 4 and n over 2. Now, because this clump resides in the very bottom, its external neighborhood has to fall inside P. Where P is the path from R to V. And since the neighborhood is large, there will be a vertex V star, which is far along path P from U. And the distance will be at least alpha n over 4. And what you get here is a cycle, and the cycle is complete as follows. You go from V star to U, then you go backwards inside U to V, and then you proceed along the path to V star. So you get a cycle, and this cycle is of length at least alpha n over 4. Okay? That's the whole proof. It's more challenging perhaps than the previous proof, but it's still 1 or 2 slides proofs. So using DFS, we can argue that we have a long cycle, and long means linear in n. And the proportionality coefficient is actually linear in alpha, which is not that bad again by this example of a very unbalanced complete bipedal graph. There, along the cycle has length alpha n, and here you get a cycle of length at least alpha n over 4. Very good. So what do we have now? So let's try to recap. So if we start with an alpha expander, what we have is a cycle of length at least alpha n over 4. On the other hand, the diameter is logarithmic, and girth is at most twice the diameter, which means we get a cycle which is fairly short. So we have a logarithmically short cycle, we have a linearly long cycle. And the reasonable question is to ask what happens in the middle. How many cycle lengths we have, and more accurately, what's the distribution of cycle lengths. Okay? So here's a statement proved by together with Elimor, and it goes as follows. Let me show you the full statement. So we have an alpha expander on n vertices. N is large enough for technical reasons. That's an asymptotic statement. And we have an interval of potential cycle lengths. This interval is linearly long. It starts at the logarithmic range. We start from c log n for some large enough constant c depending on alpha. And we end up at n divided by c. Okay? So we have a linearly long interval starting at the logarithmic range. Okay? And we would like to get a cycle of length L. Now, technically, that's impossible, because, for example, if L is odd in your graph as bipartite, you cannot quite get it. And the question is how close you can approach L. And it turns out you can approach quite close. We will have a cycle of length between L and L plus A for some particular constant A, which means what we get here is an additive approximation up to A. So the conclusion is that cycle lengths in every alpha expander are well spread. You get lots of cycle lengths, and every A in this particular interval, you get a cycle length. You cannot really predict which cycle length is there, but there will be a cycle length, a distance at most A from you. Okay? Now, the proof actually is it's very complicated, fairly complicated proof, 5-6 pages of tricks and rather complicated arguments, but the proof gives, if you try it hard enough, A, which is inverse proportional to alpha, which is the best possible order of magnitude because of this stretching argument. For the stretching argument, if you stretch every h by a factor of 1 over alpha, all cycle lengths will be divisible by 1 over alpha. And here what we get is an approximation. We can approximate every cycle length up to a factor of 1 over alpha, which is then optimal. Okay?
Do you get arithmetic progression? So could it
Well, I will discuss it in the end. It could be, we don't, well, you get an arithmetic progression just by its density, correct?
No,
But
really long. So namely, there exists an age.
sure, if I'll get to it, so one of the open questions I will possibly mention is to get, for example, a cycle length divisible by any given modulus, which we don't know to do, yes. For example, if you want to get a cycle whose length is divisible by 7c. We don't know to do it. It's probably true, but it's, we are not there yet.
Divisible
By any numbers. You,
and a long arithmetic progression will give it to you. If you just want it to be divisible by a fixed number.
yeah, that's correct. So the real question is maybe indeed to make the number this modular perhaps a function of alpha. That's true. All right.
It could even be true maybe that for every number divisible by a, for some a, if you are in this range between C of n and n over
Could be. And also, this divisibility question is a bit tricky because, for example, to guarantee a cycle of length 1 modulo 2, you cannot guarantee, correct? But maybe you can guarantee a cycle of length 2 modulo some large number. So there's a large host of questions about cycle lengths and modular numbers which are unexploited here.
You get a lot of cycles of length between L and alpha, say. How many do you get? Is it like what you'd expect?
Sure. So another question is what we get here. We get, if you look at this result, so let's estimate the number of cycles we are getting. So for every interval of length a, we get cycle length, which means we get the number of cycle lengths is the length of this interval divisible by a, at least. But the point is that this constant c comes out to be fairly horrible. It depends on alpha, on 1 over alpha exponential, and therefore what we get is a linear number of cycles, but the proportionality coefficient is exponentially small in 1 over alpha. And what we know to do, I will actually present this argument, we know to show that the number of cycles is actually polynomial, it's linear in n, and the dependence on alpha is polynomial in alpha. Okay?
If I give you some L, cycles of length between L and alpha A?
Well, theoretically can, but so if you get your expander by stretching edges, then you get a cycle length only one
not the length, just the number of the cycles.
Yeah.
You get many.
Probably get many because you can apply.
Sure. So we will get many cycles, but not. So from here you get many cycles in this particular length, but as I said, the point is that here you stop just too early. The interval length is linear in n, but the dependence of c on alpha is not the right one. Okay. Okay, so as I said, we get linear many cycles, but the dependence on alpha is bad, and there is a way to improve it. And here's the result. We know to show that for every alpha expander on n vertices, the number of different cycle lengths is linear in n, and the proportionality coefficient is not exponential like in this result here, but rather polynomial. Okay. Well, it's really hard to believe that the right answer is alpha cubed divided by log 1 of 1 over alpha, but it's still polynomials much better than getting something exponential. And actually, I will present you more or less a full proof of this result, and this proof is by pictures. And the pictures are produced by Limor. Okay. So what do? So we start actually with doing BFS here. We start with growing a BFS 3T, and we grow it exactly till it reaches alpha n over 4 vertices. Now our graph is connected because at some point, and therefore at some point of time, we will get exactly that many vertices. And now you grow your BFS3 and like DFS3 level by level, which means at that point of time we have completed a previous layer, and we are in the middle perhaps of completion of the next layer, which means we have only 2 exposit layers. Okay? Only these 2 layers have neighbors outside. Okay? Now let's look at this graph, and let's look at the graph outside of T. And the point is that if you have a set of n over 2 vertices outside of T, then it used to have by expansion at least alpha n over 2 neighbors. Perhaps part of them reside inside T, but at least half of them are outside T, which means every set of size n over 2 has at least alpha n over 4 neighbors outside of T, which means by our proposition about having a long path in alpha expander, what we get outside is a path of length alpha n over 4. Okay? So we have a BFS tree T, and we have a path of length of size alpha n over 4, and we have a path of length alpha n over 4 outside of this tree. Okay? Very good. Now, so let's look at the distances between T and alpha. So if you remember this ball grain argument, it says roughly that each one of our alpha steps you double. Okay? Which means that if you want to go from that set of alpha n over 4 to another set of alpha n over 4, you can do it in a log of 1 over alpha divided by alpha steps. Okay? So a typical distance here between these two vertices is of order log of 1 over alpha divided by alpha. And not only that, what you can find is you look at the set of vertices x, which are vertices of P, which are reachable from T by a path of this length. And you want to reach it by a path of this length, which doesn't go through any other vertex of P. Okay? And it turns out this set has to be large, because you can't really block all vertices of P by a small set, and the set X is of cardinality linear in N, and the proportionality coefficient is quadratic in alpha. So X is a set of vertices reachable by passes not passing through any other vertices, and this set has cardinality alpha squared N. Okay? And now what we do is we look at our vertex, at our tree T, and we extend it by adding k-1 layers, further layers. And the point is, if you add, and you never go through P, and the point is that once you do it, there will be, for these vertices from X, there will be a neighbor in T, that's how we defined X, and these neighbors all reside in the last k+1 levels, okay? K-1 new levels plus 2 exposed levels here, okay? And therefore, we can choose out of these k+1 layers, and k is of order log of 1 over alpha divided by alpha. We can choose the most frequent layer. Let's say it's the last one for the sake of discussion, so that we have a substantial set here along the path. Let me note it by x1. And this set x1 has neighbors at the same level of the tree. Okay? Very good, and now we are about to find lots of cycles here, and we do it as follows. We look at this set vertices in x1. We take a smallest subtree containing them, and this smallest subtree is rooted at V. Now, because that's the smallest subtree, it branches immediately, and therefore you can split these branches into two. There will be a branch which is a small one, okay? And there will be a branch which is somewhat larger, or the rest of the branches will be larger. So let's take a smallest branch, and let's take its complement, okay? And so the complement, let me note it by x2, okay? So the small branch ends up in some particular vertex u, and we need just one vertex here. And the rest of the branches, we let me note it by x2. x2 is at least 1/2 of x1, which is still a set of substantial cardinality, okay? So that's the structure. And the point is that once you have such a structure, you have lots and lots of cycles, and they're of different lengths. For example, for every vertex W here, you can see there's a blue cycle here. You immediately branch from V and go to U. Then you ride along P till you get to W, and then you go back from W to V, and because of the branching, these passes are disjoint, okay? Now, in this cycle, some lengths are fixed. For example, this length is fixed, and this is the same. This length is fixed and the same. And what differs from place to place is this difference, which means in particular that if you take different points W and W prime in this set, then you get different cycle lengths. And therefore, the number of different cycle lengths is at least as large as the cardinality of this set x2. Okay? That's how you argue about getting linearly many cycles with proportionality coefficient, which is linear, which is polynomial in alpha. So that's the whole proof. Okay, and now let me be a bit more ambitious in the remaining 10 or so minutes, and suppose we want to get all cycle lengths in an interval. Okay, we want to get a linearly long interval, and we want to get all cycle lengths in it. Now, the definition of an alpha expander does not allow for it, because, for example, if alpha expander is in bipartite graph, then every odd number we have a hole. And therefore, we need to adopt some different definition, okay? And so we need some stronger property, and this stronger property is given by some other choices, but this one is fairly natural. So the condition we are imposing as follows. We have a graph on n vertices. We have some fuzzy parameter beta. Think about beta as being some small constant, and we postulate that between every two disjoint sets A and B of size at least beta n, there is an edge. Okay? That's my definition of a graph. That's not exactly the definition of expander, because, for example, it allows for having lots of isolated vertices. If you have a complete graph of size n minus beta n plus 1 plus rest are isolates, then this definition is satisfied, and still you have lots of isolates. On the other hand, it does argue about expansion. For example, if you have a set whose cardinality is at least as large as beta n, then what this set does not say outside is of cardinality less than beta n, because otherwise you will get a contradiction with this property. Okay? So it does guarantee some kind of expansion for relatively large sets. Okay? Very good. So that's the definition we adopt. It's stronger, of course, than the definition of an alpha expander, but it also allows to reach much better result in terms of cycle length. And so here's a statement. So we have a graph on vertices, and we assume that it satisfies this property star. There is an edge between every two disjoint sets of A and B of cardinality at least beta n. And let's assume for technical reasons that beta is at most 1/20. Then you take an interval of length linear in n. Not only linear in n, it starts fairly low. It starts roughly at log n divided by log of 1/beta, and ends up quite close to n. It ends up at distance absolute constant c times beta times n from n. So it covers nearly everything. Okay. And then for every possible cycle length in this interval, there will be such a cycle. Okay? We have all cycle lengths in this particular interval. Now, these two dependencies on beta are optimal here. This one is due to isolated vertices, and this one due to existence of good expanders of logarithmic Gauss. Okay? So basically, up to the constant c here, we are as optimal as it can be. Okay? So here's a proof sketch. Good. So first of all, we need to clean G a bit. So G, as I said, might have some isolated vertices, might have some local blemishes, but what you can do, you can start with G, and you can start deleting small sets which don't expand themselves. And this deletion cannot last for longer. After at most beta n deleted vertices, what you get a graph G prime, which is an induced subgraph of G, on at least 1 minus beta times n vertices. And this graph is already a very good expander. Every set of size at most beta n expands itself outside by a factor roughly proportional to 1 over 2 beta. Okay? So if beta is small, you get a fairly nice expansion. Okay? So you start with a graph, and basically you get a an induced subgraph of nearly optimal size, of nearly full size, and this graph is already expander. Now the property star is actually a hereditary property, which means if you take an induced subgraph, the property is preserved, which means for sets of cardinality beta n and larger, we still have an expansion inherited from the previous graph. Okay? So, which means that we can start with our graph G and get a fairly good expander out of it, okay, by paying a fairly small price. Okay? Good. And now we need to embed cycles in this expanding graph G prime, and the idea would be as follows. Suppose we have some particular length L falls in this interval we would like to embed, is between logarithmic and nearly everything, somewhere in between. And we need to embed a cycle of length L. Suppose we are so lucky that we can embed in our graph the following structure. It's kind of a double-edged broom. It's a tree, T, and the tree T has this stick of length L minus 2T, actually L minus 2T minus 1 technically in terms of edges. And at the ends of it, at the two ends of it, there are k array trees for some value of k, and these are of depth T. Okay, so a stick of length L minus 2T and k array tree of depth T. And the point is, if you look at this tree and if you look at the endpoints, the leaves, you get two sets L1 and L2, and both are of cardinality at least beta n. And the claim is that if you have such a tree in your graph, then you are done because you are able to find the cycle of length L. Why is it so? It's so because we assumed, and we inherit this property from G, we assumed that there is an edge between every two sets of size beta n. And this L1 and L2 of size beta n. And the point is that the distance between every leaf here in L1 and every leaf here in L2 is exactly L minus 1. So once you add this extra edge, you are able to close the cycle. Okay, so that's a picture. So you add this extra edge, and this edge closes the cycle of length exactly L. Okay. So now the task is to take such a double-edged broom and to embed it in our graph. So we have an expander, we have a tree of bounded degree, and the question is to argue, or the goal is to argue that an expander contains a nearly spanning tree of bounded degree, a concrete nearly spanning tree, and there are tools available for it. There's a result of Balog, Chaba, Pei, and Samoti, which is in turn based on the result by Haxel, which is in turn based on the result by Friedman and Pipich, saying that you can, if you have a nice enough expander, you can embed every nearly spanning tree of bounded degree. You just take it off the shelf, you embed this tree, and once you embed this tree, you are done with it, and you have a cycle of desired lengths. Very good. So let me end it by mentioning some open questions, which are kind of fairly obvious, and some of them.
You mentioned in the beginning that you cannot expect to embed every tree because if you have the.
Sure, but I cannot expect to embed every tree in alpha expander, but here we're in a much better situation. Yeah. Yeah, so basically here, if you expect an edge between every two sets of size beta n, more or less, morally your degree should be around 1 over beta. And if beta is small, you're in much better shape. And therefore you can embed all this nice stuff, which you can note in alpha expanders. So that's the price we paid for embedding. Okay. Now, open questions to end the talk. They're kind of fairly obvious. We did prove that we have many cycle lengths in expanders. Many means linear, and the proportionality coefficient is polynomial in alpha cubed, and presumably it should be rather linear in alpha. Okay? And this would be optimal, and optimal for two disjoint reasons. One of them is having an unbalanced bipedal graph, where cycle lengths are of the size at most the smallest part multiplied by 2. And the other reason is indeed the stretching argument. If you stretch your expander, you get a cycle length which is divisible by alpha. There are two separate reasons. I don't quite see a way to put them together and to construct a counterexample, and therefore this is a plausible conjecture. The other one has been discussed. For example, what can we say about cycles of length something modulo something? Of course, we need to think carefully here what we ask. Some things are trivial, some things are less trivial. We cannot ask for cycles of length 1 modulo 2, because that's asking for an odd cycle, and they are not there.
I mean, this subdivision argument, so you can have all cycles divisible by any number you want.
Correct.
So you can never get R mod Q.
Yeah, that's true, but modulo something, you presumably you may want to take your Q to be Q is a function of alpha, correct? Yeah. On the other hand, maybe you can talk about cycles 0 mod Q, or maybe even some other number. Sometimes it's possible to get cycles of length 2 mod something, mod Q. Okay. But that's a tricky business. There are results of this sort guaranteeing cycles of given length modulo something, but usually what you do is you start with a fairly dense graph. Okay, if you want cycle of length 0 modulo Q or many lengths modulo Q, you better start with a graph whose minimal degree is at least Q. Okay, and here that's not the case. Here instead we would like to use expansion assumption to get different cycle lengths. Okay, so that's another possible direction to proceed, but let me stop here. Thank you.